Light crosses the universe as if it were born knowing the way. It streams through the silence between stars, unbroken, untiring, unafraid. Every photon begins a journey that may last billions of years, racing across cosmic oceans where no sound can follow. In the emptiness between galaxies, there is no resistance, no friction, only the purity of motion. Light is not pushed forward, it simply is forward. A wave that defines the meaning of straightness itself. Yet even as it flies, there is something unseen that watches, waiting to bend that perfect path. Gravity does not shout. It whispers in the fabric of space. It curves what light calls straight, reshapes what time calls even, and folds what seems infinite. Light, though it carries no rest mass, cannot escape geometry. Einstein's great realization was that gravity is not a force pulling on things. It is the shape of reality itself. He saw that what we once imagined as attraction, a pull between masses, was instead a bending of the stage on which all motion plays. The sun does not hold Earth by invisible strings. It curves space, and Earth follows the nearest thing to a straight line possible within that curvature. That path, which we call an orbit, is the natural motion of a world trapped by geometry. Now imagine light crossing near such a curve. It feels no tug, no push. Yet its direction changes, as though a hidden hand has brushed its course. This is gravitational lensing, the quiet artistry of space itself. A massive object, such as a star or a galaxy, bends the light passing near it, not because light slows, but because the space it travels through is no longer flat. When astronomers first saw a quasar's light duplicated into twin or even quadruple images by a galaxy far in front of it, they were not witnessing illusion. They were seeing the true shape of space made visible by the journey of light. A single quasar might appear in several places at once because its photons, taking slightly different curved routes through warped space-time, arrive at our telescopes along multiple paths. In that bending, the invisible becomes revealed. Gravity turns space itself into a lens. For light, this bending is not struggle, but obedience. It has no will to resist. It always follows the geometry before it. What we call straight is simply the shortest route through curved space-time, a geodesic. Around the Sun, that geodesic curves just enough to shift a star's position by a fraction of an arc-second, a tiny change first confirmed during a solar eclipse in 1919. But when the bending object is not a star, but an entire cluster of galaxies, the effect magnifies into vast, luminous arcs stretched across the sky. Each of those arcs tells a story written in both light and gravity. The photons began their journey billions of years ago, unaware they would be deflected. Their paths were rewritten by the weight of unseen matter, not just stars, but dark matter, invisible, yet essential. It is dark matter's gravity that sculpts these grand distortions, making it possible for astronomers to map what cannot be seen by observing how it bends what can. In the depths of space, lensing becomes both a telescope and a mirror. It magnifies distant galaxies otherwise too faint to detect, while also revealing the invisible masses that bend them. It tells us that space is not emptiness, but a dynamic field, flexible and responsive, capable of shaping light's destiny. If gravity can bend light gently, it can also bend it cruelly. Imagine the curvature deepening, the path tightening, the light's freedom narrowing until every possible direction leads inward. Somewhere beyond the quiet grace of gravitational lensing lies a darker geometry, one where the curvature becomes infinite. At first, light only arcs. Then it begins to spiral. Finally, the curves close in on themselves. Space no longer provides an escape route. No direction remains that leads away. This is the moment when gravity ceases to guide and begins to imprison. The journey of light that began as infinite motion now meets its limit. It approaches not a surface, but a horizon of meaning. the event horizon. Beyond it, space is so deeply curved that even light, the swiftest traveler in the universe, cannot return. From the outside, it looks as though light simply fades and stops. From the inside, it continues endlessly inward, toward a future it can never share with the cosmos it left behind. What began as gentle bending has become absolute captivity. The same geometry that made the planets dance and the galaxies swirl now folds upon itself, creating a region where direction and time lose their ordinary meaning. Einstein's equations predict this fate with cold precision. There, light does not die. It simply cannot find a path that leads back. Gravity, the sculptor of motion, becomes the author of darkness. And so, as the light bends further into the deepening well, the cosmos prepares for its next revelation. For what happens when space curves so completely that even light, the messenger of all knowledge, cannot escape? The story of that final surrender, where illumination becomes shadow, is where our journey now turns. Light does not know that it has crossed a boundary. It only knows the direction ahead. Yet the deeper it travels into curved space, the stranger the rules become. From far away, we imagine its path as smooth and continuous, but near a massive body, the geometry grows steep, like the inside of a funnel made of time itself. The photon, which always moves at the same speed through the vacuum, finds that the space it moves through is stretched, the time it moves within is slowed, and the meaning of straight is rewritten with every instant of its flight. Einstein's field equations describe this not with force, but with curvature. Mass tells space how to curve. Space tells light how to move. In the presence of mass, the geodesics twist inward. If you could watch a beam of light pass near a star, you would see it veer slightly, following the dip in the fabric around that mass. This deflection is small near the sun, but immense around neutron stars or black holes, where gravity approaches its strongest possible form. To imagine how light experiences this, picture space as a flowing river. The photon swims always at the same pace relative to the water, but the water itself accelerates toward the center of the current. Near ordinary stars, the current moves gently, bending the swimmer's path, but allowing escape. Near a black hole, the flow becomes torrential. At some critical distance, the inward flow of space-time moves as fast as light itself. Here lies the event horizon, the place where the river of space outruns every possible motion outward. From the perspective of the photon, nothing has changed. It still moves forward through what feels like normal space. But to an outside observer, the light seems to slow as it approaches the edge, its wavelength stretched, its energy drained into red. It never quite reaches the horizon. It simply fades, becoming ever dimmer until it merges with the blackness that surrounds it. This is not illusion, but perspective written by relativity. Time and distance themselves are relative to the observer's frame. The traveler, falling toward the black hole, experiences no pause, no stopping at the horizon. The outside universe, however, sees an infinite delay. The photon appears frozen in time, caught forever on the edge between visibility and disappearance. The curve of gravity has now become a wall of silence. Space and time trade roles. The direction inward becomes as inevitable as the passage of time itself. Once light crosses that threshold, it can no more turn back than a clock can reverse. Inside the horizon, all paths lead deeper, not because of force, but because the geometry of space-time leaves no alternative. The concept of bending light thus transforms into something far more profound. What began as an elegant proof of general relativity becomes a glimpse of the ultimate fate of motion. Gravity is not merely curvature now, it is confinement. It dictates what directions exist, rewriting the rules of causality itself. In the early universe, long before stars and galaxies, light streamed freely in every direction. Space was nearly uniform, gravity almost perfectly balanced. As structure grew, matter gathered and bent space-time around it, sculpting wells that light had to navigate. Over billions of years, the cosmos became a web of gravitational valleys and ridges. Every beam of light we see today carries the memory of that journey. Tiny shifts in color and angle, relics of the geometry it crossed. When astronomers map the cosmic microwave background, they do not see pure ancient light. They see the ghost of its bending, a tapestry of slight distortions imprinted by the gravity of galaxies that formed long after that light began its voyage. Each subtle warp is a fingerprint of the universe's hidden mass, evidence that the geometry of all things is alive, dynamic, and restless. Gravity bends not only light's path, but also our understanding of what straight even means. It reveals that the universe is not a stage set in emptiness, but an ocean whose currents define every motion within it. When light travels, it does not cross a fixed space. It traces the shifting tides of reality itself. As we follow light into the heart of gravity's dominion, we approach the place where curvature grows infinite. There, geometry consumes geometry, and time folds upon itself. The transition from bending to trapping, from path to prison, marks the birth of something entirely new. A region where light's journey ends not in exhaustion, but in transformation. For gravity, there is no boundary between grace and tyranny. The same equations that describe the gentle arc of a planet's orbit predict the total capture of light. What begins as a slow bending deepens until escape becomes impossible. When curvature exceeds all limits, when the flow of space overtakes light itself, the universe gives rise to its darkest creation. The story of light meeting gravity does not end with the bending of a beam or the dimming of a star's edge. It moves toward a collapse of meaning, a point where all that can be seen disappears beyond reach. This is where the cosmos hides its secrets, where the geometry that once revealed beauty becomes the architect of shadow. The next step in this journey is to witness that moment of birth, when the brightness of a star implodes under its own gravity, when matter's final act of fusion ends and the inward fall begins. In that collapse, gravity no longer merely bends light, it captures it. And from that capture, darkness is born. Light does not vanish abruptly when gravity wins. It fades in a slow surrender, as though the universe itself hesitates before letting go of its own reflection. Around a dying star, this farewell unfolds with an almost sacred precision. A giant once sustained by nuclear fire begins to cool, its furnace empty, its pressure gone. For millions of years it has pushed against gravity's inward call. But one day, that balance breaks. The collapse begins, and the light that once streamed outward now becomes trapped in the very well it once defined. Imagine standing, in theory only, near such a collapse. You would see the surface of the star begin to shrink, faster and faster, its glow intensifying as matter falls inward. The atoms are crushed beyond recognition, protons and electrons fuse into neutrons, and the density becomes unimaginable. The gravity deepens so quickly that space itself is pulled into the descent. In moments, what was once a living star becomes a pit in space-time, a region where curvature no longer ends. As the surface approaches the event horizon, the light from it grows redder and dimmer. From far away, it appears to slow, never quite finishing its fall. But the truth is different from what distance allows us to see. The light continues inward, though no signal can tell us so. The star passes beyond a threshold, one where escape is forbidden not by force, but by the nature of space and time. Einstein's equations tell us that this is not destruction, but transformation. The mass that once burned in radiance now defines the geometry around it. It creates a region where time itself bends inward, where every possible path leads deeper. This is a black hole. Not a hole in the ordinary sense, but a volume of space where the concept of outward loses meaning. Inside, Light cannot travel to freedom because freedom no longer exists as a direction. Around this invisible boundary, gravity performs one final act of artistry. As matter falls toward the event horizon, it spirals, heating to incredible temperatures. Friction and compression ignite it into a brief, violent brilliance. The falling gas emits X-rays, radio waves, and light far brighter than any single star could produce. The paradox of creation within destruction unfolds. The closer matter comes to disappearance, the more radiant it becomes. To an observer watching from afar, this light seems to cling to the edge, as though hesitant to cross. Time near the horizon stretches infinitely. Seconds for the falling matter become years, centuries, millennia for those outside. The photon, trying to climb away, loses energy to the climb itself, its wavelength stretched until it fades into invisibility. The universe watches, patient and merciless, as the last visible trace dissolves into darkness. What remains is not empty. The black hole is still the star's mass, still its gravity, but now concentrated into an invisible point. A singularity where density becomes infinite and the equations of physics begin to falter. The space around it remains curved, a perfect funnel of time and geometry. It is a wound that never closes, yet it defines the structure of everything near it. Light that once revealed becomes light that conceals. The cosmos, in its balance, has created a mechanism by which brightness gives birth to shadow. It is not annihilation, but metamorphosis. The photons do not die. They simply enter a region where their motion no longer connects to ours. Their journey continues inward, but inward has no return. And yet, this is not an end to the story of light. The universe holds to conservation as tightly as it holds to geometry. Energy cannot vanish. It can only change form. The energy that falls into the black hole alters the curvature, the spin, the very horizon itself. Each photon adds a whisper to the black hole's character, a record of everything it has consumed. In this sense, gravity writes memory into darkness. Every particle that crosses the horizon changes its mass, its charge, its rotation. Even when the light is lost, its influence remains woven into the shape of space-time. The black hole is whole, the sum of everything it has captured, and though we cannot see within, the surface of its horizon remembers. As time stretches, this memory becomes the only visible evidence that light ever existed there. The cosmos carries on, galaxies drifting apart, stars burning and dying, but each black hole endures as a monument to the meeting of light and gravity. They are the punctuation marks of the universe, where sentences of motion end in silence. And so, as the last rays of a collapsing star fade beyond reach, we are left not with absence, but with transformation. The path of light has become the curvature of space-time. The straight line has turned into a circle that never closes. Gravity, in its quiet power, has shown that even the purest motion can be turned into stillness. This is how gravity turns light into darkness, not by extinguishing it, but by folding its journey into the geometry of time itself. Every photon that falls into that invisible boundary continues to move forever, just not in any way the universe outside can see. The stage has been set. What began as bending has become imprisonment. The next act will explore how that imprisonment shapes the very structure of reality, where horizons form and where time slows to a crawl. Everything that falls must struggle with gravity's claim. Even light, though it has no mass, must obey the geometry that gravity creates. To understand the point where light surrenders, one must first understand what it means to escape. The story of darkness begins not with disappearance, but with the mathematics of departure. Escape velocity is a simple idea written into the heart of every planet, moon, and star. It is the minimum speed needed to break free from the pull of gravity. On Earth, that speed is a little more than 11 kilometers per second, fast enough to leave the atmosphere behind and rise forever into the sky. For most worlds, This number defines a limit between flight and fall. But as one moves through the cosmic scale, gravity's hold strengthens. On a neutron star, where a sun's mass has been squeezed into the size of a city, the escape velocity climbs to nearly half the speed of light. If you stood on its surface, a beam from your flashlight would not soar freely into space. It would bend back toward the star, forced by gravity's curvature. In such a place, light begins to feel the limits of motion. Now imagine increasing the mass or compressing the star further. The escape velocity rises higher, closer and closer to the ultimate limit, the speed of light itself. At that exact point, the boundary of freedom and captivity is reached. If the escape velocity equals the speed of light, nothing, not even light itself, can escape. This is the defining condition of a black hole. The surface that marks this critical threshold is the event horizon. It is not a physical shell, but a mathematical border, a place where the inward pull of space-time equals the outward rush of light. Anything crossing this line is forever lost to the outside universe. No message, no photon, no signal can return. To an observer far away, this edge is an illusion that seems to hold motion still. A falling object appears to slow endlessly as it nears the horizon, its light stretched into redder and fainter hues. Time itself seems to halt. Yet for the falling traveler, nothing strange occurs at all. The crossing happens quietly, smoothly, without warning. The difference lies not in the journey, but in the perspective of space-time itself. This is the essence of relativity, that time and distance are not universal, but depend on where one stands and how one moves. Near the event horizon, gravity distorts these measures beyond ordinary meaning. The same equations that describe the orbit of a planet now predict a boundary beyond which light cannot escape, and beyond which time for the outside universe becomes infinite. The idea of escape velocity can be traced back centuries before Einstein. In the late 1700s, the English philosopher John Michel and the French mathematician Pierre-Simon Laplace both proposed that if a star were dense enough, its gravity could trap light. They did not yet know the true nature of light, nor that space and time could bend, but they imagined a star so massive that its escape velocity would exceed light's speed. Their reasoning was prophetic, though it would take more than a century and Einstein's field equations to reveal the full truth. Einstein's revolution was not simply that gravity could hold light, but that gravity is the shape through which light must move. The warping of space-time creates a funnel so deep that light, always traveling at the same speed, can no longer find a direction that leads out. The photon does not slow, it runs out of geometry. The edge of escape is therefore not about speed, but about structure. Beyond the event horizon, all directions curve inward. To move outward would require exceeding the speed of light, which the universe forbids. This is the clean, silent perfection of relativity's design, that the cosmos limits itself through its own geometry. For something as intangible as light, this is a profound boundary. It means that even the purest motion can be caged by curvature. The event horizon is the dividing line between where light can still tell its story and where it is forever silenced. From the outside, the horizon appears dark, yet it glows faintly in the mathematics of space-time, an invisible sphere that holds the memory of everything that has crossed it. The physics of this boundary are both simple and strange. The Schwarzschild radius, named for Karl Schwarzschild, who first solved Einstein's equations for a non-rotating mass, defines the distance from the center of a black hole where the event horizon forms. For a mass equal to the Sun, this radius would be just under 3 kilometers. Compress the Sun into a sphere that small, and its gravity would trap even light. The equation for the Schwarzschild radius is elegant: 2 times the gravitational constant multiplied by the mass, divided by the speed of light squared. Within that formula lies the architecture of cosmic captivity. For every object, from a pebble to a star, there exists such a radius. Though for most, It lies deep within their physical body, never reached. Only when the mass collapses far enough does the horizon emerge into existence. The edge of escape is not a surface that can be touched. It has no texture, no glow, no sound. It is a threshold written in the language of space-time, invisible yet absolute. The moment something crosses it, the connection to the universe outside is severed. All future paths lead inward. And yet, even this absolute limit is not without mystery. For while the event horizon marks the boundary of no return, it also holds the potential for paradox. Later, quantum mechanics will whisper that this surface may not be entirely silent, that something may leak from its edges, faint and slow, like breath from the lungs of eternity. But that revelation belongs to another time. For now, in the vast geometry of the universe, gravity stands as the arbiter of motion, deciding which light may travel and which must fade. At the edge of escape, the cosmos writes its own boundary between freedom and inevitability. Beyond it lies not mere darkness, but the unknown architecture of a new kind of space, a realm where even time itself cannot climb free. Light does not resist gravity at the edge of escape. It simply reaches a place where geometry no longer provides a path outward. For every observer who looks upon a black hole, this boundary defines the limit of knowledge itself. Beyond it, there are no signals, no reflections, no information that can return. The universe hides what lies within behind the veil of the event horizon, an invisible frontier where time, space, and causality collapse into a single direction. From far away, this horizon appears frozen. A star falling inward seems to hover forever at its edge, its light stretching into longer and longer wavelengths until it fades from sight. The redshift becomes infinite, and the final photons reach us as whispers of energy, so faint that even the most sensitive instruments could never distinguish them. Yet, in its own frame, the star does not hesitate. It crosses the horizon in a heartbeat, continuing inward into the black geometry that defines its fate. It is this contradiction of viewpoints that makes the edge of escape so haunting. For the universe outside, time has stopped. For the infalling matter, time flows normally. Each perspective is true within its own geometry. Einstein's relativity does not choose between them. It simply allows both to coexist, each describing the same event from different regions of space-time. If we could somehow stand at a safe distance, watching this final descent, we would see the star's surface growing darker, its light dimming into invisibility. Around it, the space would shimmer with distorted starlight, a halo of lensing formed by the extreme curvature. The black hole would appear not as a simple void, but as a mirror warped by infinity, reflecting and bending everything behind it. This gravitational mirage, called the photon sphere, is the region where light can orbit the black hole multiple times before escaping or falling inward. At the photon sphere, gravity bends light by exactly the right amount to make a circular path. A photon here can circle the black hole endlessly, tracing a ring of light just outside the horizon. In practice, this orbit is unstable. A tiny perturbation sends the photon either outward to freedom or inward to capture. The photon sphere defines the last possible stand of light, the narrow ledge between existence and oblivion. Beyond this ring, time begins to behave in ways that defy intuition. Clocks placed near the horizon tick more slowly compared to those far away. To an observer distant from the black hole, time at the edge seems to approach zero speed. This is not an illusion. It is the direct consequence of gravity's effect on space-time. The stronger the gravitational field, the more it slows time's passage. This gravitational time dilation is not limited to black holes. It occurs around every mass, even Earth, though by an imperceptible amount. The clocks aboard satellites orbiting our planet tick slightly faster than those on the surface because they are farther from Earth's center and thus experience weaker gravity. Without correcting for this difference, our global positioning systems would drift by kilometers each day. In a very real sense, modern navigation depends on Einstein's understanding that time itself bends with gravity. As we approach the horizon, this bending grows extreme. The relationship between time and space becomes fluid. Directions once distinct, forward, backward, outward, lose their usual meaning. Inside the event horizon, moving outward would require exceeding the speed of light, which is impossible. Thus, all motion leads inward. Even light, which travels along the straightest possible path, finds that all those paths now end at the singularity. The singularity is the heart of the black hole, the place where curvature becomes infinite and the known laws of physics fail. Here, our equations predict densities so great and scales so small that quantum effects cannot be ignored. Yet general relativity, the theory that describes gravity, cannot speak in the language of quantum mechanics. At the singularity, these two pillars of modern physics collide, leaving a silence that no mathematics has yet fully resolved. This is what makes the edge of escape both a boundary in space and in understanding. It separates not only what can be seen from what cannot, but also what can be explained from what remains mysterious. When light reaches this frontier, it marks the limit of our theories as much as the limit of visibility. For all its mystery, the event horizon is not arbitrary. Its size is precisely defined by the mass of the black hole. Double the mass, and the radius of the horizon doubles. For rotating black holes, which most are, the shape distorts, flattening at the poles and widening at the equator. This rotation also drags space-time around with it, a phenomenon known as frame dragging. Near a rapidly spinning black hole, space itself is twisted into rotation. Nothing can remain still. If a traveler hovered near such a horizon, they would feel space itself pulling them into a whirlpool of geometry. To resist would require unimaginable energy. Even light, which can never slow down, would find its direction bent into the rotation. Some photons could gain energy and be flung outward, while others would spiral inward, forever lost. The edge of escape, therefore, is not a simple line. It is a dynamic structure shaped by mass, spin, and energy. It defines a cosmic theater where light, time, and motion perform their final act before the curtain of the horizon closes. From here, one can begin to glimpse the next step. What happens when a star reaches this boundary, when its own mass creates a horizon around it? The birth of a black hole is not merely collapse. It is the universe rearranging itself to create a region from which nothing returns. The edge of escape marks the moment before transformation, when light still exists but has already lost the possibility of freedom. Beyond this point, gravity no longer bends the path of light. It erases it from the map of the visible. What remains is the beginning of darkness, a singular silence forming where once there was fire. At the edge of escape, everything that light has ever been meets its limit. The horizon is both a physical and philosophical threshold. It separates not only what can move from what cannot, but what can be known from what must remain unspoken. If you could hover just above this border, suspended by some impossible technology, you would witness the strangest transformation in the universe. Space would seem to fall inward around you like a waterfall of time. The black hole would not be a hole at all, but a whirlpool in space-time. The stars behind it would appear distorted, their images twisted into rings and arcs by the enormous gravity. The light that should have traveled in straight lines now curves so sharply that it can loop around the black hole multiple times before escaping. What you would see is not the black hole itself, but the echo of the universe bent into its shape. As you descend closer, the pull of gravity grows unbearable. Every second that passes for you stretches into eternity for those far away. To them, you appear frozen on the horizon, fading slowly as your light loses energy. To you, the universe above accelerates, its light compressed into blinding blue. Every distant clock seems to race forward, galaxies aging, stars dying, as you fall through a moment that lasts forever. This is not illusion, it is the true interplay of space and time. Gravity slows one and speeds the other depending on where you stand. Near a black hole, the curve is so deep that time itself becomes directional. The future no longer points outward, it points inward toward the singularity. To cross the horizon is to step into a future that no longer connects to the rest of the cosmos. The mathematics of this are as elegant as they are cruel. The Schwarzschild solution describes how space and time interchange roles within the horizon. Outside, you can choose to move through time while staying still in space. Inside, the reverse becomes true. Staying still in time would mean moving outward in space, which the geometry forbids. Every possible future leads toward the center, and there is no path that allows retreat. Even the light that once defined direction loses its autonomy here. Every photon that crosses the horizon continues to move forward at the speed of light, but all forward paths curve toward the singularity. Light's freedom becomes captivity without any change in its nature. It simply follows the rules of space-time. Gravity has rewritten those rules so completely that what was once open becomes closed. For an external observer, the horizon is not a surface, but a shadow, a region where information stops emerging. The black hole's boundary becomes a kind of cosmic censorship, protecting the universe from witnessing what happens inside. Einstein's equations can describe the curvature outside perfectly, but inside the horizon they predict infinities, places where density and energy become unbounded. There, the very fabric of space-time tears. It is at this edge that the known laws of physics meet their own event horizon. General relativity tells us how gravity shapes space-time, but it says nothing about what happens when curvature becomes infinite. Quantum mechanics, which governs the smallest scales of reality, also fails here, because it cannot reconcile itself with the continuous nature of space-time. The edge of escape is therefore also the edge of understanding, a point where theory collapses as completely as matter itself. And yet, the universe continues to function with precision outside this boundary. Orbits remain stable, gravitational lensing works exactly as predicted, and time flows according to Einstein's equations. The paradox is that the cosmos operates flawlessly while hiding its most profound truths behind an unreachable veil. Black holes may be regions of no escape, but they are not entirely silent. The matter that spirals toward them forms accretion disks, rings of fire and radiation spinning at nearly the speed of light. Friction and magnetic fields within these disks generate immense heat, often outshining entire galaxies. The light from these regions does not come from within the horizon, but from just outside it, from matter's final struggle before it vanishes. Here, near the edge of escape, we see gravity's dual nature. It both destroys and reveals. The same force that traps light also makes it shine brighter before the end. Each falling atom releases its remaining energy as a last cry, turning its fall into a burst of light that can travel across the universe. The very act of being captured becomes a beacon. Astronomers studying quasars, the brilliant cores of distant galaxies, are witnessing this exact process on a cosmic scale. At the center of each quasar lies a supermassive black hole devouring matter. The radiation from the accretion disk is so intense that it can outshine billions of stars. The edge of escape, which marks the death of individual photons, thus becomes the birthplace of cosmic illumination. This is the strange symmetry of gravity. It does not simply erase, it transforms. The line where light ends its journey is also the line where the universe's most powerful light is born. The event horizon is therefore not a boundary between light and dark, but a boundary between what can be seen and what cannot, between energy that speaks and energy that falls silent. As we move forward, the story of the black hole will deepen. we will see how collapse creates not just the horizon, but the singularity, the ultimate concentration of mass and curvature. There, inside the darkness, the known laws of physics cease to function. It is the true birth of shadow, where light's destiny is rewritten not by destruction, but by geometry itself. Every star lives by a balance. Gravity pulls inward, relentless, and the heat from nuclear fusion pushes outward, defiant. For billions of years, these two forces hold each other in perfect tension, creating the equilibrium that allows a star to shine. In this balance, light is born, the steady release of energy from atomic fire, but no star burns forever. When its fuel runs out, gravity, patient and eternal, begins to win. At first, the decline is quiet. Deep within the core, hydrogen fuses into helium, and when the hydrogen is gone, the star begins to fuse heavier elements: carbon, oxygen, silicon. Each stage produces less energy than the one before. Finally, the reactions reach iron, and the process halts. Iron cannot yield energy through fusion. It marks the end of the star's resistance. Without energy to push outward, gravity tightens its grip. The collapse begins slowly, then accelerates beyond comprehension. The entire mass of the star, sometimes millions of times the mass of Earth, begins to fall inward. The core compresses, temperatures rise to hundreds of billions of degrees Celsius, and atomic structure itself begins to fail. Electrons are crushed into protons, forming neutrons and releasing a flood of neutrinos, ghost-like particles that carry away part of the star's energy. If the collapsing mass is small enough, the process halts here. The neutrons resist further compression, forming a neutron star, a sphere barely 20 kilometers across, spinning hundreds of times each second, its density so high that a teaspoon of its matter would weigh billions of tons. But if the collapsing core exceeds a certain critical mass, even neutron pressure cannot hold back gravity. The fall continues, and nothing in the known universe can stop it. This is the birth of a black hole. The collapse becomes unstoppable. Space curves inward without limit, and time itself is dragged into the fall. The surface of the star disappears behind an event horizon, that invisible boundary where escape becomes impossible. What was once a radiant sun is now a silence in space-time. The moment of transformation is violent beyond imagination. The outer layers of the star rebound off the collapsing core, creating a supernova, a brief explosion brighter than an entire galaxy. In that instant, elements forged in the star's heart are scattered into space, seeding future worlds and life itself. Iron in your blood, carbon in your cells, calcium in your bones. All were born in such deaths. Creation depends on destruction. Yet the core remains, hidden inside its own gravity. The mass continues to fall inward until it passes the event horizon. Beyond that point, our equations predict a singularity, a place where density becomes infinite, where space and time are stretched into nothingness. Whether the singularity truly exists as infinite density or as something else entirely, no one yet knows. Quantum gravity, the theory that could reveal its true nature, remains unfinished. What we do know is that outside the horizon, the black hole behaves with perfect consistency. It has only three measurable properties: mass, charge, and spin. Everything else, the details of the star that formed it, the patterns of matter that fell in, are lost to the outside universe. This is the no-hair theorem, the cosmic amnesia of black holes. They remember only how much, how fast, and how charged, but not what. It is strange to think that such a simple description arises from such a complex origin. Every photon that once escaped from the star, every atom that burned in its furnace, is gone, replaced by pure curvature. The black hole is not a thing in space, it is space itself, redefined. Its presence is the geometry of gravity made absolute. To understand how radical this transformation is, imagine compressing Earth until it became a black hole. its event horizon would be less than 2 centimeters wide. The entire planet, all mountains, oceans, and sky, reduced to a point no larger than a marble. The idea is not fantasy. It follows directly from the equations of general relativity. Every mass has a Schwarzschild radius, a size below which it would become a black hole. For most objects, this radius lies deep within the matter, unreachable. But for collapsing stars, gravity succeeds in pushing the material past that invisible boundary. In the cosmic scale, these stellar mass, black holes are the seeds of greater ones. Over time, they can merge, feeding on gas, dust, and even other stars. In galactic centers, millions of such mergers create supermassive black holes with masses equal to billions of suns. Around them, galaxies rotate like satellites bound to invisible anchors. The birth of darkness is thus also the foundation of structure. As the universe evolves, these dark cores grow and shape their surroundings. Their immense gravity gathers matter, forms stars, and drives the evolution of galaxies. Without them, the universe as we know it, with its spirals and clusters and vast webs of light, would not exist. The death of stars is not the end of creation, but its continuation. From the smallest collapse to the largest, the process follows the same principle. Gravity turns matter into geometry. The black hole is the final statement of this rule. It is not simply an object. It is a region of space-time where curvature has consumed all resistance. The very thing that once gave rise to light now gives rise to shadow. But the story does not stop with collapse. To those who watch from afar, the forming black hole still speaks in its final light. The glow of the accretion disk, the burst of the supernova, the last waves of radiation escaping before the horizon closes. These signals carry the memory of the moment gravity triumphed. And though we cannot see inside, we can infer what happens there through the language of mathematics. The singularity is the ultimate mirror, reflecting our ignorance back at us. It reminds us that our understanding of the universe remains incomplete. To truly know what lies within, we must someday unite Einstein's relativity with the strange, probabilistic world of quantum mechanics. For now, we can only watch as the last light vanishes. A star collapses, its brilliance extinguished, its mass transformed into a silence that bends the paths of galaxies. The birth of a black hole is not the death of light, but its surrender to geometry. A transformation from radiation into curvature, from motion into stillness, from brightness into memory. In the next chapter, we will linger at the horizon itself, that invisible border where light freezes and time dissolves. For it is there, at the event horizon, that reality performs its most delicate illusion, the point where something becomes nothing, yet continues to exist forever. The collapse of a star into a black hole is not a single moment, but a sequence of inevitabilities unfolding in time. Each stage tightens the grip of gravity until all resistance fails. At first, the outer layers of the dying star implode toward the core. The density climbs beyond imagination, crushing atoms into subatomic chaos. Temperatures surge to hundreds of billions of degrees Celsius, so intense that the fabric of space-time itself begins to deform. At these extremes, forces that govern ordinary matter lose their meaning. The strong nuclear force, the glue of atomic nuclei, is overwhelmed. Neutron pressure, the last defense against collapse, falters. The entire star is now a wave of falling matter, rushing toward a fate no known law can prevent. Within seconds, a boundary appears, the event horizon, though no one watching from outside will ever see its birth. The star's final light lingers just above it, fading as gravity stretches its wavelength until it merges with the darkness around it. What remains after this collapse is both less and more than what existed before. The black hole contains no surface, no core, no solid structure. It is pure geometry, a region of space-time defined by curvature rather than matter. The star's physical body is gone, replaced by an invisible shape that tells other objects how to move. When Einstein's equations are applied here, they reveal something startling. Inside the horizon, space and time swap their identities. The direction we think of as forward in time now points inward. Moving toward the singularity is not a choice. It is the passage of time itself. If we could somehow ride the collapsing matter inward, we would not see a glowing sphere surrounded by blackness. We would see the universe rushing away above us, stretched and distorted by gravitational time dilation. The closer we fall, the faster the universe appears to accelerate. In a final instant, billions of years could pass outside, galaxies could drift apart, and the cosmos itself could fade into red before we ever reach the singularity. For outside observers, the story is different. They never witness the star crossing the event horizon. Instead, they see its light slow, redden, and dim, frozen in time. The black hole that replaces it appears to form slowly, as though nature itself hesitates before completing the transformation. But this is not hesitation. It is perspective. Time near the horizon flows differently, stretched by gravity until it becomes infinite to the outside world. What happens within that invisible boundary remains one of the greatest mysteries in all of physics. At the singularity, Einstein's equations predict infinite curvature, where the density of matter and the warping of space become unbounded. Yet infinity is not a physical quantity. It is a sign that our understanding fails. Here, quantum effects must matter, for the scales involved are smaller than atoms, yet no quantum theory of gravity has yet been completed. Physicists suspect that the singularity is not truly a point of infinite density, but a region where our current theories lose coherence. Some imagine that quantum pressure, or the fabric of space-time itself, resists total collapse, creating a finite but extreme core. Others propose that information is somehow preserved at the event horizon, encoded in the surface like a cosmic hologram. These ideas remain unproven, yet they hint at a deeper unity between relativity and quantum mechanics waiting to be discovered. The birth of a black hole, therefore, is more than a stellar death. It is a statement about the universe itself, that the laws of nature can create conditions under which those same laws break down. It is a boundary between what can be explained and what must be imagined. Each time a massive star ends its life in collapse, the cosmos repeats this process of unmaking and remaking, producing an object that hides both energy and knowledge behind the veil of geometry. And while black holes appear to consume everything, they are not passive. The energy released during their formation shapes galaxies. Shockwaves from supernovae seed new stars, and jets from newly formed black holes can stretch across thousands of light years, sculpting the structure of interstellar space. From destruction comes order. The light that dies here helps build the framework of everything that will one day shine again. These newborn black holes are restless. They spin from the angular momentum of their parent stars, dragging space-time around them. The faster they rotate, the more they distort the region near the horizon, creating an ergosphere, a place where no object can remain still relative to the distant universe. Within this region, energy can be extracted from the black hole's rotation, a process known as the Penrose mechanism. Gravity, even in its darkest form, can still give back what it has taken. As centuries pass, these black holes wander through galaxies, sometimes merging when they meet. Each merger releases a storm of gravitational waves, ripples in space-time itself, that travel across the cosmos at the speed of light. Detectors on Earth have felt these faint vibrations, confirming that Einstein's predictions hold even at the brink of impossibility. Every wave we detect is the echo of a birth or collision that happened billions of years ago, a whisper from the deep fabric of creation. When we observe the universe today, we see black holes not as rare anomalies, but as essential elements of cosmic architecture. Every large galaxy harbors one at its center, and even small ones, likely contain stellar remnants from ancient supernovae. They are not exceptions to the rules of physics, but the rules pushed to their absolute limit. Gravity, patient and persistent, always wins in the end. When it grows strong enough, it bends not only the motion of light, but the shape of existence itself. Each black hole is a reminder that the universe is not static. It evolves, collapses, and renews in endless cycles. The stars that die to form them are not truly lost. Their matter, their energy, their story becomes part of a greater geometry. Thus, the making of a black hole is not a cosmic tragedy, but a transformation, the conversion of matter and radiation into spacetime's purest expression. It is the moment when light ceases to travel freely and begins to define the borders of the unseen. In that act, gravity fulfills its quiet purpose, to turn motion into stillness, energy into structure, and brilliance into the silence that shapes all things. The silence that follows a collapse is not empty. It hums with the memory of what once was, a vibration too deep for light, too patient for sound. The newborn black hole settles into equilibrium, its shape determined only by its mass, spin, and charge. Everything else, all the complexity of the star that birthed it, has vanished behind the event horizon. It no longer matters what kind of star it was, what elements it contained, or how it rotated in space. The black hole is the ultimate simplifier, turning the chaos of matter into the purity of geometry. Outside, the universe continues as if nothing extraordinary has happened. Planets orbit unaffected, the distant light of other stars drifts across the void, and only the gravitational field remains to tell the story. But near the black hole, space is no longer passive. It stretches and contracts in directions that defy ordinary sense. To fall toward the horizon is to fall toward the future itself. Every moment brings you closer not through speed, but through inevitability. A black hole's gravity is not a force in the old sense, it is the shape of time. The closer one approaches, the slower time runs compared to distant clocks. A second near the horizon might equal thousands of years far away. This slowing is not illusion, it is the literal stretching of time's fabric. The equations that govern it are the same ones that describe the gentle curve of planetary orbits and the vast arcs of light around galaxies. The difference is only in degree. In the extreme, curvature becomes destiny. In the early universe, before galaxies had fully formed, stars far more massive than the Sun were born and died quickly, leaving behind the first generation of black holes. These primordial giants acted as seeds around which matter gathered. Over billions of years, they merged and grew into the supermassive black holes that anchor galaxies today. Their existence tells us that creation and collapse were never opposites. They were two halves of a single cosmic rhythm. Matter does not vanish when it falls into a black hole. Its mass contributes to the black hole's total energy, increasing its curvature and expanding the event horizon. Even the smallest grain of dust adds to its gravity. In this way, a black hole grows not like a living thing, but like a thought, accumulating meaning from everything it consumes. Each particle, each photon, becomes part of the black hole's identity, though its individuality is forever erased. Around the horizon, space becomes a dynamic battlefield of forces. Magnetic fields twist and tear, charged particles spiral at nearly the speed of light, and radiation bursts outward in brilliant jets that can extend across thousands of light years. The paradox is astonishing. Near an object that allows no light to escape, some of the brightest phenomena in the universe are born. Quasars, blazars, and radio galaxies all draw their power from this violent borderland between gravity and freedom. If you could watch the process unfold, it would resemble a kind of cosmic choreography. Matter drawn inward by gravity forms an accretion disk, spinning faster as it approaches the horizon. Friction between layers of gas heats the disk until it glows in X-rays and ultraviolet light. Occasionally, magnetic fields channel some of the infalling matter outward instead of inward, creating narrow beams of energy that shoot into intergalactic space. These jets travel for millions of years, illuminating the structure of galaxies and carrying away part of the black hole's rotational energy. This dance of light around darkness is one of the universe's most striking contradictions. The same gravity that forbids escape creates motion so intense that it produces light of unimaginable brilliance. The edge of a black hole is both the end of light's journey and its most luminous stage. Nature, it seems, cannot resist symmetry. Inside the horizon, however, no light or signal can return. The singularity waits at the center, not a place, but a condition where the curvature of space-time becomes infinite. Here, all paths converge, all directions collapse into one. For any object that crosses the horizon, the future and the singularity are the same. This is not because of force, but because of geometry. The inward direction becomes as inevitable as time itself. We cannot see the singularity, and perhaps we never will. It may be that nature hides it perfectly, ensuring that its infinities never interact directly with the universe outside. This principle, known as cosmic censorship, suggests that the universe protects itself from the chaos beyond the horizon. Whether this is an absolute rule or merely a feature of our current understanding remains unknown. For now, we infer its presence indirectly, through its influence on everything around it. The bending of light, the orbits of stars, the radiation from accretion disks, all testify to a singular power at work. Each observation confirms that Einstein's equations hold even under the most extreme conditions, yet each also reminds us that something deeper must lie beneath those equations. A black hole is thus both an end and a beginning, the conclusion of one story and the prologue of another. It is where matter ceases to be matter and time ceases to be familiar. It is the natural consequence of gravity's perfection. The same equations that describe the gentle fall of an apple inevitably predict the collapse of entire stars. There is no cruelty in this, only consistency. The universe does not destroy, it transforms. When a black hole forms, the surrounding region becomes an archive of invisible history. The space-time curvature it leaves behind contains the memory of its creation, encoded not in light, but in gravity itself. The star's death becomes the galaxy's stability. The darkness it leaves behind becomes the anchor around which creation continues to unfold. And so, the making of a black hole is not simply the triumph of gravity, but the continuation of the cosmic story, the point where physics bends toward mystery, and where the universe, in its infinite patience, begins to write with shadows instead of light. In the next chapter, we will linger at that invisible border, the event horizon, to see how time slows, how light freezes, and how, from the outside, nothing ever truly falls. There, at the boundary between visibility and oblivion, gravity performs its most elegant illusion. There is no visible mark in space where freedom ends, yet the boundary is absolute. The event horizon is not a wall or surface, but a moment in geometry. It is the place where the curvature of space-time becomes so deep that all possible paths lead inward. From far away, it is invisible. From up close, it is inescapable. A black hole does not announce this border with light, sound, or color. It simply exists, written into the equations of relativity. The event horizon is defined not by what it is, but by what cannot cross it and return. It is the silence that answers every signal sent inward. For light, it is the ultimate horizon, the last surface from which escape is still possible. Beyond it, direction itself loses meaning. If you could fall towards such a place, you would not notice the exact instant you crossed it. The horizon has no texture, no signpost, no barrier. Space and time continue smoothly. The only clue would be that every possible path forward now leads to the singularity, and every possible way back has vanished. The fall is not resisted or accelerated. It is simply the unfolding of time as geometry demands. To a distant observer, your descent would appear endlessly slow. Your image would dim and redden as gravity stretched your light into longer wavelengths. Each second for you would take ages for those watching from afar. You would seem to freeze just above the horizon, fading gradually until you disappear. Yet this vanishing is only appearance. You would have already crossed the line, moving inward at the speed of inevitability. This strange difference in perception reveals the true nature of gravity's power. It does not just curve space, it reshapes time. The closer one moves to the event horizon, the slower time passes relative to the rest of the universe. Near enough, time almost stops. The horizon is therefore not only a border in space, but also in time. It is where the clocks of the cosmos divide into two eternities, one that can still move forward and one that can never return. Inside the horizon, the structure of reality is turned inside out. The direction inward becomes as unchangeable as the future. For anything that crosses, moving toward the center is not a choice, but a condition. There is no force pulling you there, only the fact that all geodesics, all natural paths through space-time, now converge at a single point. The black hole is not a thing that drags matter in. It is a region where the geometry of the universe insists that all motion ends in one place. Einstein's mathematics describes this perfectly, yet the experience it predicts feels impossible to imagine. Space, time, motion, and perception all merge into one continuous descent. To an outside viewer, nothing ever falls completely. To the falling traveler, the journey continues smoothly, unbroken. Both are correct. Relativity allows these two realities to coexist, each true in its own frame. This coexistence is what makes the event horizon so haunting. It is a paradox written into the laws of nature. From one side, the horizon is unreachable. From the other, it is impossible to escape. Between those views lies the mystery of what it means to exist in a curved universe. The light that hovers near the horizon never quite leaves it. Some of it circles endlessly, trapped in orbits so delicate that a whisper of motion can send it spiraling away or falling inward. This is the photon sphere, the ring of light that marks the last stand of radiance. What we see as the bright edge of a black hole in images from the Event Horizon Telescope is this very phenomenon. It is not light emitted from the hole itself, but light bent around it, focused and magnified by gravity. The black center is not a shadow cast by an object, but the absence of returning light. The photons in this ring trace paths that reveal the shape of the unseen. By studying them, astronomers can infer the mass, spin, and structure of the black hole. The image is not a photograph in the ordinary sense. It is a map of curved spacetime drawn in light. Each pixel represents a photon that traveled billions of kilometers through distorted geometry to reach our instruments. At the event horizon, time and space trade their meanings. What was once a spatial boundary becomes a temporal one. The horizon is not a place you can stand on. It is a moment you can never return from. For those outside, it is an eternal stillness. For those within, it is a future that unfolds in one direction only. This duality gives the horizon a strange beauty. It is both the end of visibility and the beginning of a new kind of order. It hides the singularity not to deceive, but to protect the rest of the universe from its chaos. It is the last smooth surface before physics itself begins to fracture. The horizon also teaches that even absolute darkness is not empty. Energy and information leave subtle imprints upon it. Each particle that falls in changes the horizon's area, its shape, its rotation. In this way, the event horizon acts like a cosmic ledger, keeping the account of everything the black hole has consumed. Though nothing escapes, the boundary still evolves, recording the story of its growth. In the next part, we will follow the behavior of time and light near this edge, where motion slows, matter burns, and even photons seem to freeze. The event horizon is not merely a barrier. It is a mirror that shows the universe. What happens when gravity writes the rules of time itself. As we draw closer to the horizon, the flow of time becomes distorted beyond recognition. What once felt smooth and steady now stretches thin, like fabric under strain. Seconds pass as hours, hours as years, and the universe beyond begins to race forward in accelerated silence. To hover near the event horizon would be to witness eternity unfold in moments. Stars would drift, galaxies would move, and the cosmic background itself would redden and fade as the ages slip by outside. This distortion of time is not an illusion or a trick of perception. It is built into the geometry of reality. According to general relativity, gravity does not simply pull. It changes the rate at which time itself flows. Near a massive body, time slows because space-time is curved. Near a black hole, that curvature becomes extreme, and the difference between one place and another becomes infinite. To an observer far from the black hole, a clock near the horizon appears to tick slower and slower until it seems to stop altogether. Yet to the clock itself, time still passes normally. This is the strange grace of relativity. Every point in space-time is locally normal, even when the universe as a whole sees it otherwise. No traveler would ever feel their time pause. They would simply cross the horizon, unaware that, from the outside, their story had already ended. If we could see the space around the horizon in perfect clarity, it would appear alive with motion. Matter falling inward does not fall quietly. It forms an accretion disk, a wide ring of gas, dust, and plasma spinning at nearly the speed of light. The friction within this disk releases colossal energy, heating the material until it glows in X-rays and gamma rays. These photons escape only from just outside the horizon, carrying the final light of matter's transformation. The view from above such a disk would be unlike anything else in the cosmos. The light bends so strongly that parts of the disk behind the black hole appear in front, warped by the gravitational lensing that curves space itself. The top and bottom edges merge into an eternal swirl of light, a circle without up or down. The black center marks not an object, but an absence, a hole in the map of possible directions. The intensity of radiation near the horizon depends on the black hole's size. A small stellar mass black hole can create bursts of light brighter than an entire galaxy. A supermassive one, like the one at the center of our Milky Way, consumes matter more slowly, its glow steady and patient. Both are governed by the same rules. Matter falling inward releases energy until it crosses the event horizon, where all signals end. This process turns destruction into spectacle. The death of matter becomes the brightest of cosmic events. Light born in violence becomes the universe's way of revealing its most hidden places. Each photon emitted near the horizon carries the signature of gravity's perfection, its path curved, its wavelength stretched, its story written in space and time. For astronomers, the horizon is not only a mystery, but a tool. By observing the light near it, we can learn about the structure of space-time itself. The motion of stars and gas near a black hole reveals its mass and spin. The pattern of X-ray flares traces how the magnetic fields twist and reconnect in the disk. Even the timing of the bursts, measured with precision instruments, provides clues to how matter behaves under the most extreme gravity known. These observations confirm again and again that Einstein's theory holds true, even where conditions seem too violent for any law to survive. Yet they also remind us that our understanding remains incomplete. Relativity describes what happens, but not why the singularity forms, nor what happens within. The horizon guards that secret perfectly. Imagine standing just above that invisible surface. Below you, time itself falls inward. Above you, the universe continues to age. Every attempt to rise upward demands infinite energy. Every effort to communicate outward becomes weaker and slower until all signals fade. The horizon is not a physical cage, but a consequence of geometry. It is the point where space flows inward, faster than light can move outward. This flow of space is not metaphorical. In the equations of general relativity, It can be described as a river of space-time rushing inward. Far from the black hole, the river moves gently. Closer to the horizon, the current accelerates. At the event horizon, the flow reaches the speed of light. Inside, it moves faster still, carrying everything toward the singularity. No boat, no photon, no signal can paddle against it. The beauty of this picture is that it replaces the idea of a force with the idea of motion. Gravity does not pull things into a black hole. It makes space itself move inward. The horizon is simply the place where that movement becomes unstoppable. Even light, which always moves through space at the same speed, is carried along because the space it travels through is itself in motion. From a distance, the black hole seems peaceful. Its pull is only strong up close, and an orbit far enough away can remain stable for eternity. Many stars live long lives circling invisible companions that are black holes. Only those that stray too near find themselves drawn past the threshold. The event horizon, then, is not just the point of no return. It is a bridge between two descriptions of reality, one where time and space behave as we know them, and one where they merge into something we cannot yet describe. It is the border between physics we understand and the physics that still waits to be written. In the next part, we will linger on the illusions that arise from this border, how light seems to freeze, how time appears to stop, and how the horizon hides what continues within. For at this edge of existence, reality is divided, not by light and dark, but by what the universe chooses to reveal and what it keeps forever hidden. To cross the event horizon is to cross a boundary that can never be crossed twice. The moment it happens, the rest of the universe slips beyond reach, and every road forward leads to the same inevitable destination. Yet nothing dramatic announces the passage. There is no shock, no sound, no sudden change. The horizon is silent because nature hides its power in geometry, not violence. If you were falling toward it, you would feel weightless. The local gravity would seem to vanish because you and everything around you are accelerating together. Space would flow with you, carrying you inward. It would be impossible to tell when you had passed the invisible threshold, for nothing marks that boundary except the fact that no light, no signal can ever travel back the way you came. From outside, however, the view is very different. Anyone watching your descent would never see you disappear. They would see your light slow, redden and fade, as if time itself had turned viscous around you. The photons leaving your body would lose energy as they climbed against the curvature of space-time, stretching into longer wavelengths until they blend with the cold glow of the universe itself. To the outside observer, you would hang forever at the edge, suspended in the frozen seconds of your final moment. This paradox, where one traveler crosses freely while another watches forever, is the purest expression of relativity. It shows that time is not universal. It belongs to the path each observer follows through space-time. Near the horizon, those paths diverge completely, one slipping inward into a private future, the other left watching a reflection that never ends. Both realities exist, and both are true. For light, the horizon is the ultimate test of obedience. It always moves at the same speed, but the geometry it travels through is no longer the same. The paths that once led outward now turn inward, curving so steeply that every photon is caught. Light does not stop. It simply loses every direction that leads away. The event horizon is therefore not a wall that traps light, but a shape that removes escape from the geometry of existence. To describe this precisely, Einstein's equations use the language of curvature, not force. In those equations, mass tells space how to curve, and space tells matter and light how to move. The horizon appears naturally as the place where the curvature of space-time becomes so deep that all possible future paths converge inward. Once there, motion forward in time is the same as motion toward the singularity. Inside, the very meaning of time changes. The coordinate that once measured distance now measures duration. To move closer to the center is no longer to travel through space, but to live through time. The singularity is not something one approaches in distance, but in the ticking of one's final seconds. Every journey ends there, not because something pulls, but because there is nowhere else for time to go. Outside the horizon, time still flows outward. Radiation escapes, stars orbit, and galaxies evolve. Yet even these distant motions are shaped by the hidden geometry of black holes. The orbits of stars around the centers of galaxies reveal invisible masses millions of times greater than the Sun. By tracing these motions, astronomers can measure black holes they cannot see. The very dance of starlight tells the presence of something darker beneath. When light grazes a black hole but does not fall in, it is bent around in great arcs. This bending, called gravitational lensing, creates the illusion of rings or multiple images of distant stars. It is the horizon's shadow stretching across the sky, the mark of unseen curvature made visible through the obedience of light. Each beam carries a record of the geometry it has crossed, whispering the shape of the darkness that bent it. And yet, for all its power, the horizon is not the end of light's story. What falls beyond it does not cease to exist. The information that defines matter and energy cannot simply vanish, for the laws of physics do not allow destruction without record. Modern theories suggest that this information might be imprinted on the horizon itself, woven into its surface like patterns on a vast invisible fabric. Each quantum of light that crosses leaves its trace, altering the black hole's entropy by the smallest imaginable amount. This idea, first proposed by Jacob Bekenstein and later refined by Stephen Hawking, changed how we think about horizons. It revealed that black holes have temperature, entropy, and even the faintest kind of radiation. The event horizon is not entirely silent after all. Though it emits no ordinary light, it may glow faintly through quantum effects, releasing energy so slow that it would take longer than the age of the universe for a large black hole to fade. At the edge of understanding, we begin to see that the event horizon is not a barrier at all, but a bridge between classical and quantum reality. It is where the smooth curvature of Einstein's spacetime meets the flickering uncertainty of the quantum world. The two theories, each perfect in its own domain, collide here in a place neither can fully describe. The horizon, then, is more than a limit. It is an invitation. It asks what happens when gravity and light, time and energy, reality and observation all converge in one equation. To study it is to study the frontier between knowledge and mystery. Beyond this border lies the singularity, where the laws of physics may dissolve completely. Yet before we face that inner darkness, there remains one more act of radiance to witness. Around every black hole burns a final halo of light, born not from within, but from what falls toward it. In that glow, the universe tells us that even at the edge of disappearance, brightness refuses to die quietly. In the next chapter, we will explore this luminous ring of sacrifice, the accretion disk, and the strange paradox that makes black holes both the brightest and the darkest objects in the cosmos. Before darkness takes everything, there is light, a light so fierce that it defies reason. Around the edges of black holes, where matter spirals into its final descent, the universe burns with its brightest fire. This region, the accretion disk, is not part of the black hole itself, but its luminous boundary, a ring of destruction where gravity and energy wage their last contest. Matter drawn toward a black hole rarely falls straight in. It carries the memory of motion, the spin inherited from the dying star, or the swirling galaxy that birthed it. As gravity pulls inward, this spin flattens the infalling gas into a thin, rotating disk. Friction within that disk, caused by particles colliding and twisting through magnetic fields, heats the gas to incredible temperatures, reaching millions of degrees Celsius. At those temperatures, atoms are stripped of their electrons, and plasma, the fourth state of matter, dominates. It radiates light across every wavelength, from visible brightness to the invisible storms of X-rays and gamma rays. The closer the gas moves to the event horizon, the faster it spins and the hotter it becomes, until the boundary between light and annihilation glows like a halo around the unseen. To watch this from a safe distance would be to witness creation turned inside out. The black hole does not emit the light, it frames it. Each photon we see is a farewell, a last message from matter that will never be seen again. Gravity takes its substance, but before doing so, it demands a final offering of radiance. This paradox defines the edge of every black hole. It is the only place in the cosmos where the brightest light and the deepest darkness exist side by side. The power released here exceeds imagination. As matter spirals inward, it converts its rest mass into energy with astonishing efficiency. A single kilogram of gas falling into a black hole can release more energy than millions of kilograms of nuclear fuel in the heart of a star. The accretion disk is a cauldron of chaos, but also a structure of beauty. The magnetic fields that thread through it act like invisible blades, channeling energy into narrow jets that shoot out from the poles of the black hole. These jets can stretch across thousands of light years, piercing the surrounding galaxies like arrows of fire. They are so powerful that they can regulate the birth of new stars, heating and stirring the interstellar gas that would otherwise collapse into more suns. The universe, in its precision, uses black holes not only as consumers, but as sculptors. The jets from their accretion disks shape galaxies, drive winds, and recycle matter into new generations of stars and planets. The light that emerges from this destruction becomes the foundation for future creation. Some of these accreting monsters shine as quasars, visible across billions of light years. They outshine entire galaxies, their brightness powered by the slow, steady fall of matter into their cores. When we look at them through telescopes, we see the ancient universe itself illuminated by the deaths of things long gone. Each photon began its journey when the cosmos was young, crossing time and distance to tell us of its origin near the mouth of infinity. The light we see from these disks is distorted by gravity. It does not travel in straight lines, but along curves shaped by the black hole's immense pull. The side of the disk moving toward us appears brighter, its light compressed into higher frequencies, while the side rotating away appears dimmer and redder. The result is a strange asymmetry, a cosmic swirl that seems to turn faster than light could ever move, yet obeys the laws of relativity perfectly. If you could hover above such a disk, the sight would be otherworldly. The black hole itself would not be black, but surrounded by rings of fire that bend over and under it, reflecting themselves in space like a mirrored infinity. You would see light circling the hole multiple times before escaping, creating ghostly echoes of the same ring, each one fainter and more delayed than the last. This glow is not eternal. Over time, the available matter runs out and the disk fades. The black hole then falls silent, invisible except for its gravity. Yet even in silence, it continues to shape the universe, warping the paths of stars and bending the background light of galaxies. Every flicker, every flare that once burned around it, remains written in the cosmic memory of space. Near the very edge of the event horizon, something extraordinary occurs. The last photons emitted just before crossing are stretched so dramatically by gravity that their energy drains into red nothingness. From afar, the light seems to hover forever, marking the boundary between visibility and oblivion. These frozen halos are not true reflections, but the final imprint of time, slowing to stillness. This is how the universe stages its most poetic performance. The matter that falls gives its final light to the cosmos before disappearing, and that light, bent and delayed, continues to travel long after its source has ceased to exist. What we see is always the past, the final seconds of a journey that ended long ago. At the edge of this radiance lies mystery. The interplay of light and gravity here is so precise that it can be described only through the language of Einstein's equations, combined with the physics of plasma and magnetic turbulence. Yet for all the complexity, the message remains simple. Nothing in the universe is wasted. Even the path to darkness produces beauty. The accretion disk is not the end of a black hole's story. It is its song, sung in radiation instead of words. Each flicker of brightness is the sound of matter surrendering to geometry, of time transforming motion into stillness. The glow before oblivion is the universe's most eloquent silence. In the next part, we will linger on those jets of energy that defy gravity's intent, the narrow, blazing streams of light that rise from the edge of eternity and pierce the cosmos. They are the proof that even where light dies, it still finds a way to travel. The jets that rise from near the event horizon are the most spectacular paradoxes in the cosmos. They are born at the edge of destruction, yet they carry energy outward across thousands of light years. Their source is not within the black hole itself, but in the furious chaos just above it, where magnetic fields twist like living threads through the plasma of the accretion disk. Imagine the matter in that disk as a sea of fire, swirling faster and faster as it approaches the horizon. The rotation drags magnetic lines of force into spirals, winding them tighter until they snap and reconnect. In those moments, energy is released with unimaginable power, accelerating particles along the poles of the black hole. The result is a pair of narrow beams that shoot outward at nearly the speed of light. These jets are not simple streams of gas. They are structured, layered, and alive with electromagnetic fury. At their cores, electrons spiral through magnetic fields, producing radiation across the entire spectrum, from radio waves to gamma rays. This process, called synchrotron emission, creates light even though the particles themselves are racing within gravity's grip. It is as if the black hole, in swallowing matter, cannot help but cry out through these luminous scars. From far away, the jets appear as thin threads piercing the dark. In some galaxies, they stretch for hundreds of thousands of light years, longer than the galaxy itself. They remain astonishingly straight, guided by the invisible geometry of magnetic fields that extend far beyond the reach of the black hole's immediate pull. When the jets collide with the interstellar medium, they create vast lobes of radio emission, colossal clouds glowing faintly against the background of the universe. These structures are among the largest single entities in existence, and yet their origin lies in a region smaller than our solar system. The energy that powers them is drawn from rotation itself. A spinning black hole can transfer its angular momentum to the plasma around it, feeding the jets and keeping them alive for millions of years. This process, known as the Blandford-Znajek mechanism, shows how even gravity's deepest wells can give back what they take. At the heart of this process lies the same rule that governs everything near a black hole. Energy can neither appear nor vanish, only change form. The black hole consumes matter, but in doing so, it radiates energy into the surrounding cosmos. It takes light inward while sending light outward. It is both devourer and creator. Astronomers studying these jets see them flicker and twist, changing in brightness over time. Their variations are not random. They carry the signature of the disk's rotation, the beat of magnetic storms, and the rhythm of matter's fall. Each pulse is a heartbeat of the accretion process, the tempo of the universe at its most extreme. Some of the light from these jets reaches Earth, traveling for billions of years before touching the mirrors of our telescopes. When it arrives, it tells stories of places where space and time nearly break. The energy of those photons is a direct message from the edge of physics itself, a message that says the universe is never silent, even where it hides its voice. At the core of a quasar, where a supermassive black hole consumes matter from an entire galaxy, the jets are so powerful that they can alter cosmic history. They can heat the intergalactic gas, preventing new stars from forming. They can sculpt the shapes of galaxies, turning spirals into ellipticals. The balance of light and shadow at galactic centers determines the fate of the stars themselves. The paradox deepens. The same process that ends the life of matter gives birth to structures that last longer than galaxies. Energy released from death becomes creation again. Gravity, the same force that imprisons light, is also the artist painting the universe's brightest images. If we could stand far enough away to see a galaxy powered by such a black hole, we would witness beauty and violence intertwined. The jets would stretch like luminous spears through the darkness, their tips glowing where they strike the cosmic medium. Around the center, the accretion disk would shine brighter than all the galaxy's stars combined. And at the core of it all, unseen, the black hole would spin quietly, its horizon smooth, its secrets sealed. The universe shows no contradiction in this. It has always turned endings into beginnings. The light that escapes from near a black hole's horizon is not light of resistance, but of transformation. It is gravity's own radiance, proof that energy never disappears, only changes its form. As we observe these jets and disks through instruments like the Event Horizon Telescope and the Chandra X-ray Observatory, we are looking into time's oldest theater. Each image, each data point is a translation of curvature into brightness. What we call radiation is the visible echo of space-time's most intimate movements. But eventually, the dance must end. The disk will empty, the jets will fade, and the black hole will fall silent once again. The light it has created will travel forever, carrying its story into the darkness. The universe will remember through the photons that never return, through the cosmic background that bears the fingerprints of every vanished flame. The glow before oblivion is not tragedy. It is ceremony. It is the universe's way of giving farewell to matter before it becomes memory. Gravity, for all its consuming nature, gives light the final word. In the next part, we will look beyond the radiance to the paradox that follows. How the black hole, once thought to be purely dark, may still emit its own faint whisper of light through quantum chance. In that whisper, the laws of the large and the small meet, and the boundary between disappearance and persistence begins to blur. The light that flares around the edge of oblivion cannot last forever. It fades, cools, and finally disappears into the quiet geometry of space-time. The accretion disk thins as its supply of gas runs out. The magnetic fields weaken, the jets lose strength, and the black hole begins to rest. From afar, it looks serene again, as if nothing ever happened, yet the memory of its radiance remains written in the space around it. Even after the last glow fades, the black hole is not empty. It holds within its gravity all the energy, momentum, and information of what it has consumed. Though nothing escapes, the universe still bears the mark of its appetite. The light that once surrounded it continues its journey outward, carrying the echo of that final brightness into distant galaxies. But the question remains: does a black hole truly keep everything it consumes locked away forever? For decades, physicists believed it did. Nothing could escape its pull, not even light. Yet the smallest details of quantum mechanics refuse to stay silent. In the realm of the very small, uncertainty rules, and even the event horizon cannot remain perfect. At this scale, space is not smooth, but restless. Particles and antiparticles appear and vanish in pairs, born from the energy of the vacuum itself. Near the horizon, one of these pairs can be separated by gravity before they have a chance to destroy each other. One particle falls inward, the other escapes outward, carrying with it a tiny amount of energy. To the universe beyond, this looks like faint radiation. To the black hole, it looks like slow evaporation. This process, predicted by Stephen Hawking, revealed something astonishing. Black holes are not completely dark. They glow, faintly and coldly, with what we now call Hawking radiation. The temperature of this radiation depends on the size of the black hole. The smaller the hole, the hotter the emission. For stellar mass or supermassive black holes, the temperature is far below freezing, invisible against the background of space. But for smaller ones, hypothetical remnants from the early universe, the radiation could be intense enough to be seen. This discovery united the two great theories that had long seemed at odds. General relativity, which describes the universe's large-scale geometry, and quantum mechanics, which governs its smallest details. At the horizon, these worlds meet. Gravity bends space, and quantum effects bend reality itself. The result is a universe that allows even the darkest objects to shine. The paradox that follows is profound. If a black hole emits radiation, it must lose mass, shrinking as it does so. Over immense timescales, it could even vanish entirely. But if it disappears, what happens to the information about everything it consumed? The laws of physics insist that information cannot be destroyed, yet the horizon seems to erase it from existence. This tension between knowledge and gravity is one of the deepest mysteries in science, the information paradox. Some theories suggest that the information is encoded on the horizon itself, stored in a pattern of microscopic quantum states. Others propose that it escapes slowly through subtle correlations in the Hawking radiation. There are even ideas that the interior of a black hole is connected to the exterior universe through hidden geometry, a bridge between space-time regions that we cannot yet see. Whatever the truth, the message is clear. Darkness is not absolute. In this faint whisper of radiation, the universe reveals its balance. Nothing is entirely lost, not even in the heart of a black hole. Light may fall inward, but its essence, its information, remains somewhere in the equations, waiting to be reinterpreted. The horizon, once thought to be the end of light, becomes instead a boundary where reality negotiates with itself. This final glow, invisible though it may be to our eyes, is the universe's quiet confession that nothing ends completely. Matter becomes energy, energy becomes geometry, geometry becomes time, and time becomes memory. Every photon that falls into darkness adds a trace to the story of space itself. And so, even as the black hole cools and the last embers of the accretion disk fade, the universe is not left in silence. The faint hum of Hawking radiation continues, slower than any human measure of time, carrying the echo of what once was. In this hum lies the ultimate symmetry. The same gravity that turns light into shadow also allows shadow to return as light. This is the glow before Oblivion's second act. Not the light of burning matter, but the soft shimmer of quantum truth. It is the bridge between the infinite and the infinitesimal, between Einstein's smooth space-time and the jittering vacuum of quantum fields. In the next chapter, we will follow this paradox further into the realm where gravity and quantum mechanics must finally meet. There, the rules of both worlds blur, and the universe reveals that even perfect darkness can shine. There was a time when scientists believed that a black hole was the ultimate endpoint of matter, the final silence of light, the one-way gate of the universe. To cross its horizon was to vanish beyond recovery. Yet the universe has never been content with absolute endings. It always leaves a trace, a remainder, a whisper. That whisper is Hawking radiation, a faint, cold quantum echo from the edge of eternity. To understand how this whisper is born, we must look closer at the vacuum itself. What appears to be empty space is not empty at all. It seethes with invisible energy. Particles and their opposites, matter and antimatter, electron and positron, photon and shadow, photon, flicker into existence and then vanish in intervals too brief to measure. These pairs appear everywhere in the cosmos, in every cubic centimeter of space, emerging and disappearing in harmony, borrowing energy from the vacuum and returning it in perfect balance. Near the event horizon, however, balance becomes impossible. One particle of such a pair may fall inward, while the other escapes outward before they can annihilate each other. The one that falls is swallowed by the black hole, carrying negative energy relative to the outside universe. The one that escapes carries positive energy away. From the perspective of distant space, the black hole has lost a tiny portion of its mass. The escaped particle becomes part of the faint radiation that we now call Hawking radiation. This process happens everywhere along the horizon, endlessly and quietly. It is not a burst of energy, not a flame or explosion, but a slow, continuous exhalation. The temperature of this radiation depends on the black hole's size. A stellar mass black hole, formed from a collapsed star, would emit radiation so faint it would take longer than the age of the universe for it to lose even a fraction of its mass. Yet in principle, the process continues. The black hole is not perfectly eternal. Over inconceivable timescales, it will evaporate, fading from darkness into nothing. Stephen Hawking's realization of this fact in the 1970s was a revolution. It connected two worlds that had long resisted unification: the smooth, geometric universe of general relativity and the jittering, probabilistic world of quantum mechanics. For the first time, gravity was shown to have temperature, entropy, and energy exchange. The horizon, once thought to be a simple boundary, became a thermodynamic surface, a place where space-time behaves like a physical substance, capable of radiating heat. Hawking's equations revealed that the entropy of a black hole, its measure of internal disorder, is proportional to the area of its event horizon, not its volume. This was the first clue to something profound. The information contained within a region of space may be encoded on its boundary. The universe itself, perhaps, behaves like a kind of hologram, with every event, every particle, every quantum fluctuation written on the cosmic surface of reality. But this discovery came with a haunting question. If black holes evaporate through Hawking radiation, where does the information about everything they consumed go? In quantum mechanics, information cannot be destroyed. It can change form, it can be hidden, but it must always exist somewhere. Yet the radiation that leaks from a black hole seems to carry no memory of what fell inside. It is perfectly random, a thermal glow with no message encoded in its pattern. This conflict became known as the black hole information paradox. If information truly disappears when a black hole evaporates, then one of the two pillars of modern physics, quantum mechanics or general relativity, must be incomplete. Either information can be lost, violating quantum law, or it is somehow preserved in a way we do not yet understand. For decades, physicists have argued across this abyss, searching for a bridge between the two truths. Some theories suggest that the information is stored in subtle correlations within the Hawking radiation itself, too faint and complex for us to detect. Others propose that it remains on the event horizon, encoded in microscopic quantum fluctuations of space-time. This idea, known as the holographic principle, suggests that our three-dimensional universe may itself be a projection from a deeper two-dimensional reality. In this picture, the black hole is not a place of loss, but of transformation. Everything that falls in leaves its trace on the horizon's surface, and as the black hole evaporates, that information is released again, spread across the radiation that escapes into space. Nothing is destroyed. It is only rearranged in a language we do not yet speak. What began as a paradox became an invitation to deeper understanding. Hawking's discovery forced physics to confront its limits. Gravity and quantum mechanics, the two greatest achievements of human thought, cannot remain separate forever. The black hole, once a symbol of cosmic finality, became instead the meeting point of all known laws, a laboratory for the unity of the universe. And so, when we speak of Hawking radiation, we are not describing light in any ordinary sense. We are describing the trembling of space-time itself. Every photon, every particle emitted from the horizon is a translation of geometry into energy, of curvature into probability. It is gravity whispering through the language of quantum mechanics. The implication is vast. If even black holes can emit light, then nothing in the universe is truly dark. The darkness we see is only the surface of processes too slow, too subtle, or too distant for us to detect. The cosmos may glow everywhere, faintly and forever, in ways we are only beginning to imagine. In the next part, we will follow this paradox to its deeper consequence: the collision between gravity's smooth continuum and quantum reality's discrete quanta. There, in the smallest vibrations of space-time, the universe reveals that even its darkest secrets are woven from light. Hawking's revelation did more than describe a faint glow from darkness. It forced a change in how we think about the universe itself. Before this idea, physicists treated space and time as smooth and continuous, a perfect stage upon which particles danced. But if black holes radiate, then space-time cannot be smooth. It must shimmer with quantum activity, restless even in stillness. This trembling fabric of reality means that the event horizon is not a silent surface. It is alive with fluctuations, with quantum waves that hold the potential for creation and annihilation. Each point on that surface becomes a messenger between the laws of the large and the laws of the small. For a black hole, these waves record every particle that has ever fallen in. For the universe, they whisper that space itself may remember everything that happens within it. To understand this, imagine the horizon not as a clean boundary, but as a thin, breathing film of quantum energy. At every instant, virtual particles emerge and vanish upon it, forming a sea of possibilities. Most of them disappear together, returning their borrowed energy to the void. But sometimes, a pair is divided. One particle falls inward, one escapes outward. The black hole loses a fraction of its mass, and a ripple of radiation drifts away through space. This is not heat as we know it. It is not the warmth of atoms colliding, but the statistical shimmer of curved space-time. Its temperature is so faint that it would make the coldest vacuum seem hot by comparison. A black hole of the sun's mass would radiate at a temperature less than 1/10,000,000th of a degree above absolute zero. For supermassive black holes, the temperature is even lower, almost absolute zero itself. Yet over the longest stretches of cosmic time, even such faint warmth becomes significant. If we wait long enough, longer than the lifespan of stars, galaxies, or atoms, the black hole will evaporate. It will release its mass as energy, one quantum at a time, until only a whisper remains. The largest ones will outlive the current age of the universe by unimaginable factors, yet even they will fade in the end. The night sky of the far future will not sparkle with stars, but with the cold radiation of dying black holes. This process may seem slow, but in it lies one of the most elegant balances of nature. A black hole, born from the collapse of matter, slowly gives that matter back to the universe as radiation. It is the cycle of energy written in its most patient form. Every gram of mass that falls in will eventually reappear as light, spread thin across space and time. The realization that black holes can evaporate has led physicists to consider their ultimate fate. When the mass becomes small enough, the temperature rises sharply, for small black holes radiate faster than large ones. The final stage of evaporation may be a burst of energy, a last flash of light carrying away the black hole's remaining essence. After that, nothing remains, only radiation and the geometry that once held the hole's memory. Yet that memory may not be lost. The key lies in the nature of quantum information. Every particle emitted as Hawking radiation is entangled with something that fell into the hole. This entanglement forms invisible connections across the horizon. If the radiation carries even a fraction of this information outward, then the universe preserves the record of everything that has ever happened, however faintly. This idea has reshaped not only astrophysics, but the very foundations of quantum theory. It suggests that the universe itself may be a single, vast, entangled system, a web of correlations stretching across time and space. The black hole, once the symbol of isolation, becomes instead a point of communication between all that exists. Hawking's paradox continues to deepen. If information escapes, then the black hole is not truly a prison but a slow translator. If it does not escape, then quantum mechanics, the most successful theory in science, must be incomplete. In either case, the truth must be more intricate than either theory alone. Somewhere between the continuous flow of gravity and the discrete jumps of quantum mechanics lies a single, unified description of reality. Modern physicists have begun to glimpse that unity in theories like ADS-CFT correspondence, a mathematical idea that connects gravity in a curved spacetime to quantum fields living on its boundary. In this framework, a black hole in one description is equivalent to a hot, glowing fluid in another. Information that falls into the hole is preserved in the quantum state on the boundary. The holographic principle emerges again, suggesting that our universe may be like a projection from a deeper informational surface. If this vision is correct, then light is never truly lost to gravity. It is transformed. The darkness of a black hole is not a destruction, but a rewriting of information into a new form: geometry, curvature, and radiation. The laws of physics remain intact, but their meanings change depending on where we stand. Every photon emitted through Hawking radiation carries not only energy, but also a trace of order, a subtle fingerprint of what came before. In that sense, the black hole is not an end, but a storyteller. Its evaporation is a slow confession, a return of knowledge to the universe in whispers too faint for us to yet hear. The true wonder of Hawking's insight lies not in the radiation itself, but in what it revealed about the unity of nature. Gravity, quantum mechanics, thermodynamics, and information theory, once thought separate, are all aspects of the same cosmic language. The black hole is the sentence where these words meet. In the next part, we will step beyond the mathematics and follow the philosophical current that flows beneath it. What does it mean for the universe to remember? What does it mean for light, once trapped, to return as probability? Hawking's paradox is not only a question of physics, it is a question about the nature of reality itself and whether darkness is ever truly dark. The paradox that Hawking revealed has never truly closed. It only deepened, stretching into a question not just of physics, but of philosophy. What does it mean for something to exist if it can no longer be seen? If light can escape only as probability, not certainty, then what remains of the concept of being? The black hole, once an object, becomes a verb, a process by which the universe rewrites itself. In Hawking's equations, the steady loss of mass is not destruction, but conversation. The black hole speaks to the vacuum, trading bits of energy and information across its boundary. The process is slow, but relentless. Each particle emitted is a syllable in that cosmic whisper, a note in a dialogue between gravity and quantum mechanics. To the physicist, this whisper carries mathematical elegance. To the philosopher, it carries something more haunting, a suggestion that even in perfect darkness, reality is still thinking. It is still aware of itself through the geometry of information. The radiation itself is almost unimaginably faint. A black hole the mass of a mountain would glow at a temperature close to room temperature. A black hole of stellar mass would glow colder than space itself. Yet if the black hole were smaller, one formed perhaps in the first instance after the Big Bang, its radiation could be fierce, bright enough to flash before fading into nothingness. Such primordial black holes may have been born in the density waves of the early universe, though none have yet been found. The idea that they could exist shows the scale of Hawking's insight. He did not merely describe an effect, he revealed a principle that applies everywhere. Every horizon, not only those of black holes, but of the expanding universe itself, carries a temperature. Every region of spacetime has entropy. In this sense, the entire cosmos is a kind of thermodynamic system, forever balancing energy and information, creation and loss. From this idea grows a larger understanding. The universe is not a static stage, but a living computation. Every process, every motion of light or matter is a calculation performed by space-time itself. Black holes are not errors in that computation. They are memory nodes, dense, silent regions where information is stored in ways we do not yet know how to read. Hawking's paradox forces us to confront the limits of perception. If we can no longer tell whether something truly vanishes, then perhaps nothing ever does. The boundary between existence and non-existence becomes as flexible as the boundary between space and time. The horizon is both a beginning and an end, both a wall and a mirror. In this mirror, we glimpse an unexpected symmetry. The laws that create black holes also seem to describe the birth of the universe. In the earliest moments after the Big Bang, space-time itself expanded from a region where quantum effects and gravity were indistinguishable. The mathematics that govern Hawking radiation also apply in reverse to the creation of cosmic inflation. The beginning of everything and the end of everything may be reflections of one another. The universe, it seems, has always been speaking in pairs: creation and collapse, expansion and contraction, radiation and absorption. Each black hole may be a small echo of the first instant of time, a private universe whose beginning is hidden behind its horizon. In some speculative models, what falls into one black hole could even emerge elsewhere, in another space-time region, through a tunnel of geometry that we call a wormhole. Such ideas are not yet proven, but they reveal how deeply Hawking's insight reshaped imagination itself. When we look at a black hole now, we do not see an absence. We see an equation written in light and silence. We see the meeting point of everything we know and everything we cannot yet describe. Hawking radiation reminds us that no horizon is final, no boundary complete. Even the deepest darkness participates in the grand cycle of exchange that defines the cosmos. In the end, what Hawking showed was not that black holes shine, but that reality itself is more subtle than any division between light and dark. To radiate is to remember. To evaporate is to give back. To vanish is to translate existence into a new form. When the last black hole in the universe finally fades, trillions upon trillions of years from now, the final photon it emits will carry the last whisper of this paradox. It will drift through a cosmos gone cold, the last trace of curvature, the last note of a song gravity began before time itself. And in that final shimmer, there will still be light. Light and time are twins, born of the same law. Wherever light travels, time follows, and wherever time slows, light bends. To understand gravity is to see how the universe teaches these two to move in rhythm, curving together through the fabric of space-time. Einstein showed that gravity does not pull on light as a force, but reshapes the path that light must take. When a beam passes near a massive star or galaxy, it follows the curved geometry around it, just as a river follows the bend of the valley. This bending is not a distortion of light itself, but a revelation of the space it moves through. The first proof came in 1919, when astronomers during a solar eclipse saw starlight deflected by the sun's mass. The stars appeared displaced, as though the sky had shifted. That moment confirmed Einstein's general relativity and changed how humanity saw the cosmos forever. Everywhere in the universe, light carries the fingerprints of gravity. When it escapes from a deep gravitational well, it loses energy, stretching into longer wavelengths. This is gravitational redshift, a softening of light's voice as it climbs from the depths. Time, too, stretches in this process. A clock near a massive object ticks slower than one far away, and the photons that leave it carry that slow rhythm as a mark of their origin. This slowing of time is not a trick of measurement. It is woven into the structure of reality. Gravity bends not only space, but time itself. And because light always travels at the same speed, it must adjust its wavelength and frequency to match the local geometry. The redshift of light is thus the echo of time's dilation, the visible sign that the universe does not keep a single universal clock. In the vast cosmos, gravitational lensing magnifies these effects into beauty. When light from a distant galaxy passes through the gravity of another along its path, the light bends into arcs, rings, or mirrored images. Astronomers call these Einstein rings, and they are nature's own telescopes, focusing light that would otherwise never reach us. Through them, we can see galaxies that formed when the universe was young, their light bent but not broken, their messages delayed but not lost. The bending of light also reveals mass we cannot see. Around galaxies and clusters, the pattern of distortion in background light betrays the presence of dark matter, invisible substance that outweighs all visible stars combined. It does not shine, but it bends light as gravity demands. Through lensing, we have mapped the skeleton of the cosmos, tracing unseen filaments of dark matter that bind galaxies into a cosmic web. On smaller scales, near black holes and neutron stars, these same principles become extreme. Light can orbit a black hole several times before escaping, forming the glowing ring captured in the image of M87 star, that luminous halo around nothingness. Each photon in that ring has traveled a path shaped entirely by the bending of time and space, curving through gravitational wells that twist its direction until it emerges to meet our telescopes. Time near such gravity slows to almost stillness. If you were to hover near the event horizon, distant galaxies would seem to accelerate, their clocks racing ahead, their light shifted into blue before fading away. From their point of view, you would appear frozen in place, your own clock ticking infinitely slow. Both are true. This is the symmetry of relativity. There is no single now, only local moments stitched together by geometry. The first darkness in the universe was born not of absence, but of redshift. When the cosmos expanded after the Big Bang, light from the early plasma stretched until it cooled into invisibility. The glow of that era remains as the cosmic microwave background, a fossil light that still fills space in every direction. It is the oldest image in existence, not of stars or galaxies, but of time itself when it first learned to move. In this grand expansion, gravity and light have always danced in tension. Gravity tries to pull the universe inward, while light, through its pressure, tries to push it apart. Their balance defines the fate of all things. The bending of light is thus not a side effect of gravity, but the visible form of this eternal struggle, a reminder that curvature and motion are inseparable. When light bends, it carries history with it. Each deflection is a record of where mass lies, of how space-time is shaped. The universe, through this bending, becomes a lens looking at itself. Photons that left the first galaxies billions of years ago arrive to us curved and delayed, telling the story of everything they passed along the way. To watch this bending is to witness time folding. The light we see from a distant quasar may have left before the sun was born, only to be curved by the gravity of galaxies that did not yet exist when it began its journey. Every observation of the sky is an act of looking backward, not into space, but into the past. The night is not a field of distant points, but a layered structure of memory, with each photon a page from an earlier chapter of time. The redshift of light tells us the universe is still expanding, still cooling, still carrying the echo of its own beginning. The cosmic background that once burned white hot now glows faintly in microwaves, stretched by billions of years of cosmic breathing. Light itself has aged, and with it, time has changed meaning. And so, the bending of time and light is not only a phenomenon, but a dialogue between what was and what will be. Each beam of light curves because time curves. Each slowing of a clock echoes in the stretching of wavelengths. Together, they form the grammar of space-time, a cosmic language that tells the story of gravity's poetry. The deeper truth is that gravity does not trap light out of cruelty. It simply follows the logic of geometry. Light, obedient to space-time, always moves straight, but straightness itself is curved. To live in such a universe is to exist within the bend, to see every photon as a messenger from a different time, and to understand that darkness is never emptiness, but simply light too long delayed. In the next chapter, we will meet the shadow that proves all this bending is real, the silhouette of a black hole itself, captured by the combined eyes of Earth's telescopes. There, light completes its longest journey, circling the edge of time before falling into silence, leaving only its glowing trace around the void it cannot escape. For centuries, black holes were invisible equations, ideas that could not be seen. Their existence was certain, yet their appearance was unknown. Then, in the early 21st century, humanity looked into the heart of galaxy M87 and saw the impossible. The first image of a black hole's shadow. It was not a photograph of the hole itself, for nothing can be seen beyond its horizon. What we saw was the light around it, twisted into a glowing ring by gravity. This image, produced by the Event Horizon Telescope, was the work of hundreds of scientists linking radio observatories across Earth into one vast instrument. Together, they formed a telescope as large as the planet, capable of resolving the finest details in the universe. The black hole in M87 is a giant with a mass of 6.5 billion suns. The light that orbits it takes days to complete a single circle. The glowing ring we see is not the event horizon, but the photon sphere, where light itself is trapped in endless orbit. Inside that ring lies the shadow, the absence formed by light that falls inward and never returns. To create the image, astronomers did not take a simple picture. They collected radio waves, the long whispers of light invisible to our eyes, and combined them through interferometry, aligning signals from telescopes separated by continents. Each telescope recorded data with atomic precision, and together, those fragments of light interference were woven into a single image, a map of curved spacetime drawn by the photons themselves. The result was more than proof. It was revelation. The shape of the shadow matched Einstein's predictions almost perfectly. It was circular, smooth, and defined by the geometry of a rotating black hole. Even the brightness around its edge confirmed relativity's subtle details. The side rotating toward us glowed more intensely, its light compressed by motion, while the far side dimmed, stretched by redshift. What humanity saw that day was not an object, but a phenomenon, gravity revealing itself through light's obedience. The black hole's shadow is not a thing, but a region where the paths of light turn inward, where time curves so steeply that escape becomes impossible. Yet the photons just outside that boundary trace a final orbit, forming a luminous halo that outlines the edge of invisibility. This shadow is not confined to M87. The same technique has since been applied to Sagittarius A star, the supermassive black hole at the center of our own Milky Way. Its image, smaller and more dynamic, showed a similar ring, glowing with the heat of captured gas and plasma. In both cases, light from matter falling inward was bent, lensed, and delayed, creating the same cosmic fingerprint, a ring of radiance encircling silence. The significance of these images reaches beyond astronomy. They are direct visual confirmations of space-time curvature, evidence that Einstein's geometry is not metaphor, but reality. What we see is not the black hole itself, but the shape of light as it obeys the universe's most fundamental equation. Each photon in that image has lived an extraordinary life. It may have circled the hole multiple times before escaping. Its path may have been bent, reflected, or delayed by years relative to its neighbors. Yet together, those photons compose a single moment of understanding, light and gravity in perfect conversation. The brightness of the ring reveals temperature, motion, and magnetic structure. The shadow reveals mass and spin. Together they tell us not only what a black hole looks like, but what it is doing. The data show that these cosmic giants are not still. They are engines of motion, converting infalling matter into radiation, their spin stirring magnetic fields that shape the fate of entire galaxies. When we look at the shadow of a black hole, we are seeing the boundary between the visible and the unseeable. The light we detect comes from plasma heated to billions of degrees, whirling at near the speed of light. Yet what defines the image is the dark region, where time no longer moves outward. It is a portrait of the universe's most elegant contradiction: brightness giving shape to darkness. The shadow reminds us that even in absence, there is structure. The black hole's geometry dictates where light may exist and where it may not. The circular edge is not drawn by matter, but by the shape of space-time itself. To gaze upon it is to see time bending into its own reflection. As we refine our instruments, future images will show more detail. The flickering arcs of plasma, the twisting of magnetic fields, the shifting glow as matter falls and disappears. Each new image will bring us closer to understanding not only black holes, but the nature of reality itself. For if we can see the shadow of gravity, we may one day see the pattern of space-time that connects all things. The universe is filled with such shadows. Every galaxy hides one at its heart, silent and massive, shaping the stars around it. They are not monsters, but anchors, holding the fabric of the cosmos in place. The shadow is the mark of order, not chaos. It is gravity's signature, the outline of the infinite written in light. And yet, for all their finality, these shadows still change. When black holes merge, their horizons ripple, sending out waves in space-time itself, gravitational waves that travel across the universe, bending time as they pass. We have detected these waves too, the tremors of collisions billions of years old. Together with the shadows, they complete the picture. The universe made visible not only through light, but through the motion of time. In the next chapter, we will leave the individual shadows and look at the cosmos as a whole, at what happens when all the light is gone and only darkness remains, when black holes themselves become the last architects of reality. There will come a time when the last star burns its final fuel, when the galaxies that now shimmer like islands in a vast sea will grow dim and the universe will fall into quiet. This future is not myth, but mathematics, the natural conclusion of thermodynamics written across billions upon billions of years. The story of light will end, as all things end, in gravity's embrace. Stars are born from clouds of hydrogen and dust, their light fueled by nuclear fusion. But fusion cannot last forever. As each star exhausts its fuel, it cools, expands, and dies. Some fade gently into white dwarfs, others collapse violently into neutron stars or black holes. Each death adds to the growing collection of darkness. In the far future, when even the smallest red dwarfs have cooled, no new stars will be born. The age of starlight will be over. When that happens, the universe will belong to black holes. They will consume what remains: wandering planets, dead stars, clouds of gas, everything that drifts too near. Gravity, patient and relentless, will gather all the scattered remnants of matter into its silent chambers. Galaxies themselves may eventually dissolve, their stars flung apart by cosmic expansion, leaving only the central black holes drifting in the dark. These remnants will continue to merge, colliding in cosmic slow motion. When two black holes meet, they spiral together, releasing gravitational waves that ripple across space-time. Each merger creates a larger, more massive hole, fewer in number but greater in strength. Over unimaginable spans, the universe will simplify, trading complexity for depth, exchanging light for shadow. Even then, the story of light will not be entirely finished. As black holes merge, they send out the last great flashes of energy in gravitational form, waves that carry the imprint of their collision. These waves do not fade as ordinary light does. They stretch and weaken with the universe's expansion, but they never vanish completely. Long after the last photon is absorbed, the faint tremor of space-time will remain, a record of motion written in the structure of existence itself. Physicists call this distant future the black hole era. It is a time beyond comprehension, when the universe is old beyond measure and the night is eternal. The remaining black holes, vast and cold, will slowly evaporate through Hawking radiation, losing mass at a rate too slow to imagine. The largest of them will survive for 10 to the power of 67 years before finally dissolving into faint light. When those final moments come, each black hole will flare softly, like a dying ember releasing its last warmth to the void. The energy released will be small, but pure. Photons, neutrinos, and particles of every kind drifting outward into the expanding dark. This will be the final light of the universe, the echo of all creation, the whisper of matter returning to balance. After that, there will be only radiation, stretched so thin by expansion that it can no longer interact with anything. The universe will continue to grow, but nothing new will form. It will reach a state called heat death, maximum entropy, complete uniformity, perfect stillness. Time will continue to pass, but no events will occur, for there will be nothing left to change. And yet, in that silence, the legacy of gravity remains. Every photon that ever existed, every curve of light and space, will still exist in principle, encoded in the frozen fabric of space-time. The universe will not be gone, it will only be quiet. This is not tragedy, but fulfillment. The laws of physics demand that energy cannot be destroyed, only transformed. Light becomes matter, matter becomes gravity, gravity becomes radiation. The cosmos is a closed conversation with itself, repeating its message in different dialects. What we call darkness is only one of those dialects, a quieter, slower form of light. Perhaps the most haunting truth is that time itself may lose meaning in that distant age. Without change, time has no measure. Without energy exchange, there is no before or after, only the infinite now of the universe at rest. Gravity will have done its work completely, but some theories suggest that this may not be the final word. Quantum fluctuations, the same restless activity that gave birth to Hawking radiation, may someday spark new beginnings. In the endless emptiness, a small region of space could inflate into a new universe, as our own once did. If so, the death of this cosmos would be the birth of another, and the cycle of light and gravity would begin again. Whether that happens or not, the lesson of cosmic darkness remains. Everything that begins in brightness must end in stillness, but the ending is never absolute. Gravity is not a destroyer, but a transformer, turning light into memory and memory into silence. In the far future, when no eyes remain to see, the last photons will still drift across the infinite, carrying the imprint of all that ever was. And though no one will watch them fade, their existence will still matter, for they are proof that even after eternity, the universe remembers. In the end, all things return to simplicity. The universe began in light and ends in silence, and between those two extremes lies the story of gravity. It is not the story of destruction, but of transformation. The shaping of time, the bending of space, and the turning of brilliance into shadow. When the last black hole evaporates, when even the faintest radiation fades into invisibility, the universe will have reached its quietest state. But this silence is not emptiness. It is balance, the perfect equilibrium between energy and geometry. The vast expanding nothingness will be the final expression of gravity's work, the smooth flattening of all curvature, the fading of all contrast. If we could watch that moment from outside, we would see nothing. No stars, no galaxies, no motion. And yet, the equations would still hold. The laws that govern the birth of the first atoms, the collapse of the first stars, and the radiance of quasars would still describe this final void. The universe ends not because the laws fail, but because they complete themselves. It is a strange destiny. Gravity, The force that once pulled matter into suns and bent light into spirals becomes the agent of rest. In the long decay of energy and motion, gravity's hunger consumes everything, not through violence, but through inevitability. Its curve becomes shallower as the universe expands until it flattens into stillness. But to call this an end is to misunderstand. The universe is not erased, it is distilled. What remains is not nothingness, but the simplest possible form of everything, pure space-time, stretched so wide that no further change can occur. Entropy has reached its maximum, and time itself dissolves into geometry. In that geometry lies memory. Every particle that ever existed, every wave of light that ever crossed the void, has left its pattern in space-time. These patterns may never again be read, but they remain imprinted in the structure of reality. The final universe is not a blank canvas, but the sum of everything it has been. Philosophers once asked whether light defines reality. The answer is yes, but incompletely. Light gives us visibility, but gravity gives that visibility meaning. Without gravity, light would never curve, never form stars or galaxies, never give birth to life. It would travel straight forever through a featureless void, unobserved and unremembered. Gravity turned that light into story, into structure, into history, into time itself. And so, when light meets gravity, it does not die. It transforms. It becomes time, matter, and eventually darkness. Darkness is not the opposite of light, but its evolution, the form it takes when stretched beyond endurance. Every black hole, every bending of light, every fading of a star is a verse in this cosmic poem. The universe is both author and audience, writing its tale in photons and gravity waves, erasing and rewriting endlessly. We are a fleeting line in that story, made of light slowed into matter, existing between the brightness of birth and the silence of return. To understand this is to find peace with the vastness. The same gravity that will one day unmake us also made our existence possible. The same laws that bend light into shadow also allow consciousness to arise and witness them. In every act of observation, we give gravity's silence a voice. Perhaps that is the final meaning of it all. The universe does not vanish into nothing, it becomes reflection. Light, once freed, finds itself folded back into the geometry that gave it birth. The end is not death, but symmetry. The curve completed, the equation resolved. And if someday another universe rises from quantum stillness, it will begin again with light. The same photons, reborn in a new space-time, will race outward once more, painting the first dawn of a new cosmos. Gravity will follow, curving their paths, shaping their destinies, turning light into life and life into understanding. Until that day, we live in the middle of the story, between creation and silence, between light and gravity. And as we look at the stars, we see not only their brilliance, but also their fate. Gravity does not kill light, it transforms it, folding brilliance into silence and time into shadow. Every black hole is not an absence, but a reminder. Even light cannot escape the geometry of fate.